Hello, my name is Mike Fiedler. Welcome to this recording on Autodesk Fusion 360 simulation. Today we're going to go through a validation example. It's a static stress analysis of a flat circular plate. Since this is the first recording that I am doing for this channel, I should introduce myself. Again, my name is Mike and I am an Autodesk employee. This is not part of any Autodesk promotion. The reason that I'm doing this is because I do like to teach finite element analysis, and I don't have the opportunity to maybe as much as I'd like to. And so I'm just doing these kind of on my own. And I am going to largely do validation examples. And the reason that I'm going to do that is really twofold. One, because we have a known theoretical solution, I like that we can set up the problem. And if something comes out wrong with the results, then there's a good chance, we set something up wrong. And it's just a matter of finding out what that is. And in fact, I did that when I was first going through this model, realized that I had the dimensions of the geometry incorrect. So what should have been the radius I had used as the values for the diameters. So after making that correction, hopefully this will all turn out. The second thing that I like about the validation examples is we know that if we set it up correctly, then the program, what we expect of the program is to give us the appropriate results. So it's also a good way to check and make sure that the program is working correctly. I'm also envisioning that maybe if you are just getting started or considering the Autodesk Fusion 360 product, this is maybe a way to gain some confidence with the results of the program. Certainly everybody wants to know that the program they are using can be trusted. So we'll take a look at various validation examples and hopefully you see that it's easy to use and is producing the results that you would expect it to. So here is our model. I'm not going to go through the modeling or design environment portion of it in this video. We're just going to focus on the simulation end. We could do a little bit of modeling if that is of interest. There are a lot of videos out there on modeling, maybe not so much on simulation, which is another reason that I chose to focus on the simulation specifically. Let's take a look at the description for this model. It is a Rourke and Young problem, so if you have the 5th edition, you can reference page 334, table 24, case 1A. It is a flat annular circular plate of constant thickness. The inner radius is 12 inches. The outer radius is 24. The thickness is defined as 0.5 inch. The modulus is 27.5 E6, Poisson's 0.3. As far as constraints, the outer edge is simply supported, the inner edge is free, and the load will be located at that inner edge. In the setup of this, it is described that the load is a 50-pound force per inch load. What we want to do is apply that as a force. So I calculated the circumference of the inside circular region, 2 pi r, and you can see we get a length of 75.398 inches. So that tells us that the total force there, multiplying that 50 pounds force per inch by the length, would give us a total load of 3,769.9 pounds force. Since we are doing a quarter model, we don't want to apply that total force. We want to apply 1/4 or a quarter of that force, which means 942 pounds force. So that's what we will be applying to our model as a force of 942. And then hopefully we come up with the theoretical results. Hoop stress at the inner radius should be 22,340 and the vertical deflection of 0.4. So let's go ahead and take a look how we do this in Fusion. So again, right now I'm in the design workspace. Let's toggle over to simulation. As I go into simulation, I can choose what analysis type I want. Again, this is going to be a static stress. And I can just start to define things across the top row along the ribbon bar. Those things that I add will also be added into the browser. So the study we've already defined is a static stress analysis. You can change it if you accidentally choose a wrong analysis type. You can go into manage settings and right there's a drop-down menu. That's one way to do it. Simplify allows you to simplify your model, remove fillets and chamfers, simplify some complex geometry into a simpler shape, things like that. And that simplification is strictly impactful to your simulation analysis. It does not change your original design model. So that's great if you have multiple people working on the same file, or you want to maintain your design file to create production drawings, but you know that you want to simplify your simulation model. Pretty simple geometry we have here, so we don't have to worry about simplification. The materials from the pull down menu, I'm going to select the study material. You'll see that it has a steel property to it. And if I select that row and click on properties, we can see what those values are, pretty typical steel properties. From this example, they gave us a different or unique Young's modulus. So I've already created a material and I dropped that into a library that I created. So at the bottom here, I'm going to go ahead and change that library. I named that library Fusion Validation Library. And then if I scroll over to the study material, or the material I want to use for this study, I named that material V1. So let me select that material from the list, and now you can see there's the Young's modulus that the problem description had, 27.5 E6 or 2.75 E7. Poisson's ratio is 0.3. The rest of the properties are here because I chose that steel material, and then I just edited the material properties that I needed to edit, primarily Young's modulus. So we'll say OK to that. Moving on from materials are constraints. And we can do structural constraints. We can do bolt connectors, rigid body connectors. I'm going to select structural constraints, and it was defined on the outside edge of this geometry that it was going to be simply supported. So if you reference the mini axis up here, what we're going to do is just give that a Y constraint on that edge right there, and we'll say OK. Now, having done that, I get a little kind of a lock symbol. It's not a closed lock. It would be if I had constrained all three directions, but we're just constraining the Y direction. So it's kind of an open lock symbol there for you. Now, remember, this should be a full 360-degree plate, and we just did a quarter of it. So what you have to do there are symmetry constraints, and you select the faces where you've cut through the material, and you constrain the translation that's perpendicular to that face. So if I rotate the geometry around a little bit, I can see that the Z direction, or Z axis, is perpendicular to this face. So I'm going to go constraints. I'm going to uncheck X and Y, and I'm just going to leave Z fixed, and we'll select that face and say OK. Which means this face over here is the one I'm going to constrain in X. So we'll just rotate the geometry around a little bit, and I'm going to select UX. And whoops, I got an edge. So I'm just going to hit the X button, make sure I'm highlighting the face. There we go. And I'll say OK to that. So we have added a few things into our model now. And if I expand the items in the browser, I can see there's the material that I added to it. And if I expand the load cases, we don't have any load on the model yet, but there are the constraints that I've added. So if I need to edit any of them, I can just hover over that little pencil icon and click it and bring it up to edit it. Next would be our load. So from the drop-down menu, there's a number of loads right there. Or if I select structural loads, again, there's a variety of loads here. So I'm going to select the force, select that edge right there. And there are different ways that you can define the directions. Normal, you can tell it it's at an angle. I like to use the vectors so I can define my loads precisely and along specific axes. So in the Y direction, we want to go with a load of minus 942, whatever we calculated here, 0.478, and we'll say OK. So there is our force. I don't need to worry about contacts because this is a single part. I don't have to worry about that, maybe in a future example. The meshing, we can right-click and tell it to generate the mesh, or if I were to just go ahead and solve the model, it will do that meshing for me. So we'll do that as a first pass. There are two options with Fusion 360 for the solve. I can choose to solve it on a cloud, on the cloud, which will send it to a server farm, do the computation and send the model back. Or I can choose to solve it locally. We'll solve it first locally. So we'll show you both experiences. And when I do it locally, you can see it goes through preparing, generating contacts, meshing, and solving. So even though I didn't specifically do anything with the mesh, it does do the mesh as part of that process. And solve, and now I'm in the results. And when we come into the results, it gives me this little pop-up dialog, which tells me a little bit about the safety factor. So it is giving me an orange warning symbol that the safety factor is a little bit low. We're not too worried about that. I'm going to dismiss it. And the way that you change results is over here by the legend. And I'm going to change it to take a look at the displacements. And there's our displacement, 4174. Specifically, if I look in the y direction, we have a 4173. If I bring back my spreadsheet, we compare those values, we can see we're a little bit off, right? 42, 47, 41, 73. Not terrible, but a little bit off. So when your displacements are not matching, generally that's a indication of, presuming everything else is correct, an indication that maybe the model is not meshed well enough. So we are going to go with a little bit finer of a mesh. Let's display the mesh. Just click that icon. You can see that it's a rather coarse mesh. And in addition to that, you can see, notice the transition, say, from the darker green to the lighter green fading into yellow here. You notice how it kind of follows this line of the mesh. When you see results follow the mesh like that, that's generally an indication that it's not meshed well enough. If I toggle into a stress, you can really see it here, right? I would expect the stresses along the inner diameter here, or inner radius, to be rather smooth, and instead you see that it's kind of what we would call hot spots or higher stress, and then a region of lower stress, higher stress, lower stress. So my model is not meshed quite well enough. So what I'm going to do is just say finish results, and we'll take a look at those mesh details. First of all, some of you I know right now are saying, hey, I don't want to have to worry about the mesh. I want the program to figure all that out for me. Can it do mesh convergence? And the answer to that is yes, it can. So if you go to Manage and Settings, and we go to Adaptive Mesh Refinement, it's off by default. But if I set it to low, for instance, you can see there it's going to do a maximum number of 2 refinements. It's going to look for a convergence tolerance of 20%. 20% of what? Of whatever result you have down here to select. So if the von Mises between 2 subsequent mesh attempts, mesh analyses, is less than 20% change in von Mises, then it will kick out at that point. And then you can see as we go further, then it increases the number of refinements it'll do and makes that tolerance tighter. I'm not going to use that for this model. I know that it's a 1/2 inch thick, so we're just going to specify our own mesh size. So I just went to the pencil icon and mesh, and you can see there's a slider. So it starts out at 10%. Of course, moving it towards the 1%, that's going to make it finer and finer and finer. The other thing I can do is specify an absolute mesh size. So instead of using the slider, I'm going to tell it I want a 0.25 inch mesh size, and we'll say OK and generate the mesh. And there it is going through the meshing process. Now this one, of course, is certainly going to be a finer mesh. You can envision what 2 elements through that thickness looks like. There you go. So this one will send off to the cloud. It's a little bit finer. Maybe I don't want it using up the resources on my computer. Maybe I have other things to do. So I'm going to go ahead and tell it to solve on the cloud. The nice thing about solving on the cloud also is if you have multiple load cases or you have multiple studies, maybe study 1's a static stress, maybe study 2 is a thermal, maybe study 3 you combine them and do a thermal stress analysis. You can set all those studies up, and then if you're choosing on the cloud, you can just click the boxes over here and tell it what studies you want it to solve, and they'll all be sent off to the cloud. You don't have to worry about it. You could shut down for the day if you want. Next time you open up your computer, open Fusion, open up this model, it'll download those results for you. So let's go ahead and see what that looks like. Let me go ahead and say solve 1 study. And you can see that right there, then we get some progress that it's sending it. And now it is scheduled to be solved. So as soon as it finds a available machine that it's able to do the computation on, then it will begin that analysis. So we should see that toggle here pretty soon. And then once that analysis is complete, it will send it back. So I'll go ahead and be quiet here for a moment so we can watch that progress. Okay, so that didn't take long. That was less than 30 seconds from the time that I stopped talking when it was sending or had started the waiting for a machine to solve on until it brought the results back for us. So let me go ahead and close that, and I'm going to go ahead and close this results window. And now immediately we can see that the stresses are a lot smoother here, right? We don't see that dark to light, dark to light, dark to light. They transition out across the diameter of the part as I would expect them to. So let's go ahead and change to a displacement. And again, we'll go with a Y displacement. So the Y displacement here is 0.4246. So if I plug that into my spreadsheet here, minus 0.4246, hit enter, that's a 0.02% difference. Not 2%. I've already done the computation to make it into a percent difference, multiplying it by 100. So it's 0.02% different than what the theory tells us that should be. So we got good results or good correlation there. And the last thing we have to check is a hoop stress. So I'm going to go with a stress. So for that, we can take a look at the normal stress either in the Z direction or X direction. So I'm going to choose stress, and then from the pull down menu, we'll choose a normal X direction. And I can see that we're getting a value there of 22,377. So let's plug that in, 22,377. And we get a percent difference of 0.164. So that looks good as well. So very good agreement there once we refined our mesh a little bit, and pretty simple model to set up. Again, it's 12-inch inner radius, 24-inch on the outer radius, thickness of a 1/2 inch if you want to try and replicate that. Modulus at 27.5 E6, Poisson's 0.3, and the load was 942.478 pounds force, and it all looks good. So hopefully that is helpful, and I hope to do more of these so you can see again how to work with Fusion 360, learn a little bit about simulation, and have confidence in your results. Thanks for watching.